Here is something nobody tells you about the most asked question in cosmology. Physicists are not refusing to answer it because they want to seem clever. They are refusing to answer it because the universe, as best as anyone can currently measure it, does not have the structure the question assumes. There is no outside, there never was. And tonight, I want to walk you, slowly and carefully, through exactly why, from Hubble at his telescope in 1929, to a horizon-eating reality away from us right now, to the strange new idea that space itself may not even be the bottom layer of what is real. So grab your blanket, hit subscribe, get cozy, and stay until the end, because the question you came in with is about to be replaced by a much stranger one. Let's ease into it. Part 1. The question that shouldn't exist. There is a question that almost every human being asks at some point in their life, usually late at night, usually after someone has casually mentioned the Big Bang, or shown a documentary clip of galaxies drifting apart on a black screen. The question always arrives the same way. It feels obvious. It feels like the most reasonable follow-up imaginable. And it goes like this. If the universe is expanding, what is it expanding into? The question feels like it should have an answer. It feels like the kind of thing a physicist could explain in about 30 seconds if you just sat down with one over coffee. After all, expansion is something we understand. We watch it happen every single day. Smoke from a candle expands into the air around it. A balloon expands into the room. An explosion expands outward, pushing into whatever space happens to be in its way. Every example of expansion we have ever seen in our entire lives, from the moment we were born to the moment we sat down to watch this video, has involved one thing growing into another thing, something hot pushing into something cold, something dense pushing into something thin, something here pushing into somewhere else. So when someone tells you the universe is expanding, your brain does what brains do. It reaches for the nearest familiar pattern. It assumes there must be an outside. It assumes there must be a somewhere else for all of this to expand into. It assumes the universe is sitting inside a larger container, and as the universe grows, it must be filling more and more of that container, like a pot of boiling water rising toward the rim. The question, what is the universe expanding into, feels like it must have an answer, because every other expansion you have ever observed has had one. And here is where modern cosmology does something almost cruel. It does not answer the question. It refuses the question. It tells you, in the politest scientific language it can muster, that the question itself is malformed, that the question assumes a structure of reality that does not exist, that you have been carrying around your entire life, a model of space and time that simply does not match what physics has discovered about the actual universe you happen to live inside. There is no outside. There never was. The Big Bang, that explosive birth of everything we can see and everything we cannot see, did not happen at a place. It did not have a location. It did not occur somewhere that you could, even in principle, point to on a map. It happened everywhere at once, in a space that, as far as anyone can currently tell, was already infinite, the very moment it began stretching. The expansion you are hearing about is not motion through a larger arena. There is no arena. There is no stage on which the universe is performing. The universe is the stage, and the audience, and the actors, and the theatre itself, and there is nothing on the other side of the walls because there are no walls and there is no other side. I want you to sit with that for a moment, because it does not land the first time you hear it. It does not land the second time either. The human brain is built for containers. We evolved on a planet where everything has an inside and an outside, where every river has a bank, every forest has an edge, every box has a lid. Our brains were not shaped by the savannah to picture geometries with no boundaries. Our intuitions were not built to handle systems that contain no exterior. When you imagine the universe expanding, your mind almost cannot help itself. It pictures a glowing ball in a black void, getting bigger, pushing outward, eating up more of the dark. That image is wrong. It is so wrong that physicists have spent the better part of a century trying to find ways to explain how wrong it is without making the listener feel insulted. The mismatch between the way our brains work and the way the universe actually behaves is the entire problem. Cosmology is, in a very real sense, a discipline that requires you to abandon almost every container metaphor you have ever used. It asks you to imagine a system that has no exterior. It asks you to picture a geometry that has no embedding. It asks you to accept that the question, what is the universe expanding into, belongs to the same family of questions as, what is north of the North Pole? The answer is not a location. The answer is not a thing. The answer is, the question is malformed. There is no north of the North Pole because once you reach the pole, every direction is south. The grid of latitude and longitude that organized your thinking simply runs out. Asking what is north of north is not a hard question. It is not even a question. It is a noise that resembles a question because it follows the grammar of one. And the question of what the universe is expanding into is the same kind of noise. It sounds like a question. It has a subject and a verb and a target. But when you push on it, when you actually try to specify what kind of thing the universe could possibly be expanding into, you find that the words come apart in your hands. There is nothing for them to refer to. Now, I want to be careful here, because none of this is semantic trickery. This is not a riddle. This is not a play on words. Physicists are not refusing to answer the question because they want to seem clever. They are refusing to answer the question because the universe, as best as we can currently measure and model it, does not have the structure the question assumes. This matters. This is not about how we talk. It is about what reality is. And once you start to understand why the question fails, you start to understand something genuinely new about the cosmos you happen to live in. Here is what I am going to do over the next stretch of this video. I am going to take this question apart, layer by layer, the way you would take apart an old machine to see how it works. I am going to start with what most people think the Big Bang was, and I am going to show you how that picture fails. Then I am going to show you what actually happens when space expands, and how the math behind it does something that sounds illegal until you look at it carefully. Then I am going to show you that the universe has no center, no edge, and possibly no boundary of any kind. I am going to show you that what you call the observable universe is not the universe, but a kind of fog. I am going to show you that the expansion is accelerating, that there is a horizon out there right now, eating reality away from us in real time, and that there are entire galaxies whose light will never, ever, no matter how long you wait, reach this planet again. And then, when we are deep enough in, I am going to show you the part that even physicists are still trying to make sense of. The part where space itself may not be a fundamental thing at all. The part where geometry might be something that emerges from quantum entanglement, like temperature emerges from molecules. The part where the question, what is the universe expanding into, becomes not just unanswerable, but unaskable, because the thing it asks about may not even be the bottom layer of reality. By the end of this, the question is not going to have an answer. I want to be honest with you about that up front. You are not going to walk away with a satisfying line you can repeat at parties. What you are going to walk away with is the feeling that the question has been replaced. The question that opened this video is going to dissolve, and a different question is going to take its place, a stranger one, a deeper one that physicists themselves do not yet know how to answer. So let me ask it again, slowly. And let me ask it knowing that you are now paying a different kind of attention. If the universe is expanding, what is it expanding into? Hold that question in your head. Let it sit there. Because the moment we start looking for the answer is the moment the universe starts looking very, very different from anything you have ever pictured it being. Part 2. The explosion that never happened. The first thing you have to give up, before any of the rest of this makes sense, is the picture of the Big Bang as an explosion. I know, that is hard. The name itself is the problem. Somebody, decades ago, picked the words Big Bang almost as a joke, almost dismissively, and the words stuck. And now every diagram you have ever seen of the early universe shows a glowing point erupting outward into a black background. The image is so common that it has become the default. When most people think of the start of everything, they picture a kind of cosmic firework, a flash of light blooming out into a waiting darkness, hurling matter in every direction at unimaginable speed. That image is wrong. Almost every part of it is wrong. There was no flash in a darkness, because there was no darkness for the flash to occur in. There was no point in space that erupted, because there was no surrounding space for the eruption to happen inside. There was no center that the explosion radiated from, because there was no center anywhere, in any direction, full stop. Whatever the Big Bang was, it was not a thing happening inside space. It was something that happened to space itself. This is the first major shift you have to make in your thinking, and it is the one that, if you can really feel it in your bones, makes the rest of the journey easier. An explosion is matter moving through a pre-existing space. A bomb detonates, and the shrapnel moves outward into air that was already there. The space the explosion occupies existed before the explosion did. The space outside the explosion exists during it. The space that will eventually contain the dispersing debris is sitting there waiting before any of it begins. An explosion needs a stage. The Big Bang did not have a stage. The Big Bang was not matter moving through space. The Big Bang was the universe itself, the entire fabric of space and time, in a state of extreme density, beginning to evolve. The galaxies are not flying outward from a central point. The galaxies are sitting roughly where they have always been sitting, locally speaking, while the geometry between them stretches. That is a very different thing. It is so different that using the word explosion in the same sentence as the Big Bang is technically a little bit of a lie. We say it because the alternatives are clunky. We say it because the truth is harder to picture, but it is, in a real sense, misleading. So how did we figure this out? Because nobody just woke up one morning with a fully formed theory of cosmic expansion. The story of how this picture came together is a story about a man, a telescope, and a strange pattern in the light from distant galaxies that should not have been there. In 1929, an astronomer named Edwin Hubble was working at the Mount Wilson Observatory in California, using what was at the time the largest telescope in the world. Hubble had spent years staring at faint smudges in the sky that we now call galaxies, but which, at the time, were still called nebulae, because nobody was quite sure what they were. Some astronomers thought they were clouds of gas inside our own Milky Way. Others suspected they were something far stranger, entire other galaxies sitting at distances so vast that the human mind could barely process them. Hubble, by carefully measuring certain pulsing stars inside these nebulae, had already settled that question. They were galaxies. They were enormous. They were millions of light years away. But then Hubble noticed something else, something that quietly changed everything. When he looked at the light coming from these galaxies, he saw that the wavelengths of that light were stretched. The signature patterns of certain elements, the spectral fingerprints that astronomers use to identify what stars are made of, were all shifted toward the red end of the spectrum. We call this redshift. And the further away the galaxy was, the more its light was shifted. Not a little, not occasionally, systematically. The further out you looked, the more the light had been stretched. There was a clean, almost insultingly tidy relationship between distance and redshift, and that relationship turned into what we now call Hubble's law. The recession velocity of a galaxy, how fast it appears to be moving away from us, equals a constant times its distance. What does that mean in plain language? It means every galaxy in the universe, more or less, is moving away from us, and the further away it is, the faster it is moving. Picture that for a second. Pick a direction in the sky, any direction, and the galaxies in that direction are receding. Pick the opposite direction, same thing. Look up, look down, look sideways. Every patch of sky tells the same story. We are sitting still, and the entire cosmos is fleeing away from us in every direction. Now, if you stop right there, you might be tempted to think we are at the center of something. That would be the natural assumption. If everything is running away from you, you must be standing at the spot they are running away from. But that is not what is happening. And this is one of the most beautifully strange parts of the whole picture. Every galaxy in the universe sees the same thing. If you were standing on a planet in the Andromeda galaxy, 2.5 million light years away, and you looked at the sky, you would see exactly the same pattern. Distant galaxies receding. The further away, the faster. From every vantage point in the universe, every other vantage point appears to be running away. There is no privileged location. There is no spot you could stand in and say, here, this is where the expansion started. Every observer everywhere sees themselves at the apparent center of an expanding cosmos. This is the geometry that breaks intuition the first time you encounter it. It is not perspective. It is not an illusion of standing somewhere unusual. It is a literal geometric property of the universe. The expansion is not happening from a point. It is happening between every pair of points. Pick any two galaxies in the sky and the distance between them is increasing. Pick any other two and the same is true. The growth is not radiating outward from a source. It is, in some sense, everywhere at once. Every patch of space is getting bigger relative to every other patch of space, and there is no origin of the process you can point to. This is where the explosion metaphor falls apart for good. An explosion has a center, a bomb has a location. The shockwave moves outward from a definable point. But the expansion of the universe has none of these features. It is centerless. It is locationless. It is not a thing happening at a place, because the thing happening is happening to all places at the same time. So if there is no center, and there is no point that the expansion is radiating from, what exactly is expanding? What is the thing that is changing? Because something has to be doing the changing. The galaxies are not, mostly, flying through space. So what is going on between them? What is the it in the sentence, the universe is expanding? Hold on to that question, because the answer changes everything. And once you see it, you will not be able to look at the night sky the same way again. Part 3. The first conceptual break. To understand what is actually expanding, you have to step into the framework that makes sense of all of this, and that framework is general relativity. Albert Einstein worked it out over about a decade, finishing the core equations in 1915, and what he produced was not just a theory of gravity, but a theory of space and time themselves. Before Einstein, physics had treated space the way a stage manager treats a stage. It was the place where things happened. It had no behavior of its own. It just sat there, fixed, immovable, neutral, providing the backdrop for matter and motion. Newton's universe was, in essence, a vast and rigid grid through which planets and apples and cannonballs travelled. Einstein looked at that picture and threw it out. In general relativity, space is not a passive backdrop. Space has structure. Space has properties. Space can curve. Space can stretch. Space can warp around heavy objects, bending the paths of light and the orbits of planets. Not because some invisible force is pulling on them, but because the geometry they are moving through is itself curved. Gravity, in this picture, is not a force at all. Gravity is what you experience when you move along a straight line through a curved geometry. The Earth orbits the Sun not because the Sun is yanking on it, but because the Sun has bent the space around it, and the Earth is just rolling along the lowest path through that bent landscape. That much you may already have heard. But to understand expansion, you need to take it one step further. You need to understand that the geometry of space is described by something called a metric. A metric is, in essence, the rule that tells you how to measure distance. It is the mathematical object that says, if I am here and you are there, this is how far apart we are. In flat, ordinary space, the metric is the rule you learned in school. The distance between 2 points is the square root of the sum of the squares of the differences in coordinates. Pythagoras, basically. In curved space, the metric is more complicated, but it still does the same job. It tells you what distance means at every point. Now here is the move that unlocks the whole story. The metric is not fixed. The metric can change, and in our universe, the metric is changing. Specifically, the metric has a scale factor in it, a number that grows with time, and, as that scale factor grows, the distance between any 2 points in the universe increases, even if neither point is moving in any local sense. That is what expansion is. It is not motion through space. It is the metric of space itself evolving, with distances getting larger because the rule that defines distance is shifting. This is the conceptual break. This is the part where you have to let go of the picture of galaxies flying outward and replace it with something stranger and, ultimately, more accurate. The galaxies are mostly sitting still. Their local velocities, the actual motions of stars within galaxies and galaxies within their local neighborhoods, are quite modest. Andromeda is even moving toward us. The reason distant galaxies appear to recede is not that they are speeding away through some pre-existing arena. The reason is that the space between us and them is growing. The geometry that defines the meaning of distance between here and there is, in real time, increasing the distance, even though neither of us is going anywhere. Imagine you and a friend are standing on a long sheet of rubber, very still, neither of you walking. Now imagine someone, somewhere, is gently pulling the rubber sheet outward in every direction. You and your friend would slowly drift apart, not because either of you was walking, but because the sheet you were standing on was stretching beneath you. That is, in a rough analogy, what is happening between galaxies. The sheet is stretching. The galaxies are the marks on the sheet. The marks are not moving relative to the sheet, but the sheet is getting bigger, and so the marks end up further apart. This shift in framing also explains something that, on first hearing, sounds completely impossible. The most distant galaxies we can observe are, in a very real sense, receding from us faster than the speed of light. Yes, you heard that correctly. There are galaxies whose recession velocity, calculated from the rate at which the metric is stretching between here and there, exceeds the speed of light. And no, this does not violate Einstein's relativity. Relativity forbids matter from moving through space faster than light. It does not forbid space itself from stretching at any rate it wants. The galaxies are not moving through space at faster than light speeds. The space between us is simply growing fast enough that the effective separation rate exceeds light speed. Nothing is actually traveling that fast. No information is moving faster than light. The geometry is just doing what geometry does in an expanding universe, which is whatever it pleases. This is one of those facts that sounds like a loophole or a trick, but it is not. It is a clean consequence of taking general relativity seriously. Velocity, in the sense of motion through space, is one thing. Recession due to expansion is a different category entirely. They get measured in similar units. They look superficially alike. But under the hood, they are not the same kind of process, and one of them is bound by the cosmic speed limit, while the other simply is not. So now you can see why the original question is in trouble. The universe is not expanding in space. The universe is expanding as space. There is no arena in which the expansion is occurring. The expansion is a property of the arena itself. Asking what the universe is expanding into is like asking what color the number 7 is. The question takes a property that applies to one kind of thing and tries to apply it to a thing of a totally different category. But this just pushes the question one level deeper. If space itself is doing the changing, then what, exactly, is space? What is the thing that is stretching? Because if the metric is evolving, then the fabric described by the metric must be something. It has structure, it has behavior, it responds to matter and energy. It curves and stretches and ripples when massive objects move through it. So it cannot just be nothing. It cannot just be the absence of stuff. Space, whatever it is some kind of something. And that something does not have an edge. That something does not have an outside. That something, as we are about to see, may not even be located in any larger container of any kind. The expansion of the universe is not the universe pushing into a void. It is the universe being a different kind of thing than the void model assumes. And as you start to follow this thread, the picture only gets stranger. Part 4. The Big Bang happened everywhere. Now we come to the sentence that, the first time you hear it, sounds like a contradiction. The Big Bang did not happen at a point. The Big Bang happened everywhere. Every location in the universe, every single one, was once part of the hot, dense state that we call the early universe, including the spot where you are sitting right now, including the spot in the middle of the most distant galaxy you can see, including any spot you can imagine, anywhere, in any direction. All of those spots were, at the same moment in time, packed into a state of unimaginable density and temperature. The Big Bang was not a place that the universe came out of. The Big Bang was a moment in time across all of space. This is the sentence that, more than any other, turns the original question to dust. If the Big Bang did not happen at a particular place, then there is no direction you could fly in, no matter how long you traveled or how fast, that would take you toward where it happened. Where it happened is here. Where it happened is also there. Where it happened is everywhere, simultaneously, the entire universe at once, in a denser and hotter configuration than anything you could possibly construct. The universe did not start small and grow. The universe started everywhere and stretched. Let me make this concrete, because it is one of those ideas that benefits from being said in 3 or 4 different ways before it really sticks. Imagine the universe today. Imagine all the galaxies, all the stars, all the empty space between them, the whole cosmos as it currently is. Now, run the clock backwards. As you do, the metric shrinks. The distances between galaxies get smaller, not because the galaxies are flying inward toward a central point, but because the rule that defines distance is, in reverse, contracting. Every pair of points gets closer to every other pair of points. Eventually, if you keep rewinding, the matter in the universe is squeezed into a state where the densities are enormous and the temperatures are extreme. Eventually, the equations of general relativity, by themselves, run out of road. They tell you the density goes to infinity, which is a sign not that the universe was actually a point, but that we have hit the edge of what our current theory can describe. The crucial thing is that during this rewind, every region of the universe is participating equally. The patch of space you are sitting in is being compressed along with every other patch. The spot 50 billion light-years away is being compressed along with every other spot. There is no special location that is being squeezed harder than the rest. Every point is going through the same evolution. So when you reach the early state, the hot dense plasma we call the primordial universe, that plasma is not concentrated somewhere. It is everywhere. The entire universe is the plasma. The plasma is the entire universe. There is no room outside of it because there is no outside. And here is the part that breaks people's brains, and I want you to really sit with it for a second. If the universe is infinite now, and it almost certainly is, or close enough that the difference does not matter, then it was infinite then. There was never a moment when the universe was finite in size. The early universe was not a tiny ball that grew. The early universe was an infinite expanse of hot plasma whose internal distances were small. That is a totally different thing. An infinite expanse with small internal distances is still an infinite expanse. You cannot reach the edge of it because there is no edge. You could fly forever in any direction and never get out because there is no out to get to. This is the part where the balloon analogy, which physicists use constantly because it is genuinely useful, also starts to mislead. You have probably heard the balloon explanation. Imagine the surface of a balloon. Draw dots on it. Inflate the balloon. The dots move apart. The surface gets bigger. None of the dots is at the center because the center of the balloon is not on the surface. Every dot sees every other dot moving away. It is a beautiful analogy, and it captures a lot of what we need to capture about cosmic expansion. The dots are the galaxies. The surface is space. The inflation is the expansion. And critically, the center of the balloon is not a place on the surface, just as the center of the universe is not a place in the universe. But the analogy has a sneaky problem, and the problem is the balloon itself. A balloon exists in three-dimensional space. The surface of the balloon is curved into a higher dimension. The balloon is sitting in a room, surrounded by air, embedded in an external geometry. When you picture the balloon, your brain naturally pictures the room around it. And then your brain goes, so the universe is like a balloon, which means the universe is sitting inside something larger, just as the balloon sits inside the room. And that is the part that is wrong. There is no room. There is no embedding. The mathematical structure of the universe does not require any higher dimensional space to live in. The geometry is self-contained. It does not need to be inside anything to exist. That is hard to picture, because every curved surface you have ever seen in your life has been embedded in something. The surface of the Earth is curved, but it is curved within three-dimensional space. The surface of a saddle is curved, but it is curved within the space around it. We have no everyday experience of a curved geometry that exists by itself, with no surrounding arena, but mathematically, such geometries are perfectly well defined. You can describe a curved space using only the relationships within the space, without ever reference to anything outside it. The curvature is intrinsic. It is a property of the space itself, not of how the space sits inside something else. And the geometry of our universe, as best as cosmology can tell, is exactly that kind of intrinsic geometry. It has shape without context. It has structure without surroundings. Try to hold that for a moment. An infinite, three-dimensional space, expanding, not into anything, not surrounded by anything, not embedded in anything, just expanding in the sense that every internal distance is growing. Picture yourself standing in the middle of it, except that there is no middle, because every spot is equally central. Picture the space stretching away from you in every direction, except that the stretching is not pulling things away from you, it is increasing the rule that defines distance, so the same numerical separations now correspond to greater physical distances. There is no edge you could ever reach. There is no boundary you could ever bump into. You could travel forever in any direction and you would only ever encounter more universe, more galaxies, more space, more of the same self-contained geometry, stretching as you went. This is what cosmologists mean when they say the Big Bang happened everywhere. It is not a poetic statement. It is a literal geometric fact about the model. The hot, dense state was a property of all of space at a moment in time, not a localized event in some larger arena. There is no outside that the universe came from. There is no place beyond the universe that the universe has been pushing into. The universe is, as best as any of our equations can tell, simply itself, a self-contained geometric system whose internal distances are growing. So the original question, What is the universe expanding into has now had its assumptions stripped away one by one. There is no center, there is no edge, there is no embedding, there is no outside. The universe is not a thing inside a larger thing. The universe is, in the most literal sense available to us, all of the space there is. But we are not done, because there is still a question worth asking, even with all of those assumptions removed. Is the universe actually infinite, or is it finite but unbounded? Is it flat, or is it curved in some subtle way? And does the answer to that question tell us anything about what kind of system we are actually living in? Part 5. Flat, infinite, or worse. If you ever want to feel humbled by what we have managed to measure as a species, look at the numbers behind the curvature of the universe. In the early 2000s and through the 2010s, a satellite called the Planck spacecraft sat in orbit and stared out at a faint glow that comes from every direction in the sky, a glow called the cosmic microwave background. This glow is the leftover radiation from when the universe was about 380,000 years old, when it had cooled down enough that photons could travel freely for the first time. When you look at this glow with sensitive enough instruments, you can see tiny temperature variations in it, fluctuations of about 1 part in 100,000. The pattern of those fluctuations encodes an enormous amount of information about the geometry of the universe, including its overall curvature. When you analyze that pattern carefully, you can extract a number called the curvature parameter, written as omega k. If omega k is positive, the universe has positive curvature, like the surface of a sphere generalized to 3 dimensions. If omega k is negative, the universe has negative curvature, like a saddle. If omega k is 0, the universe is flat, not flat like a pancake. Flat in the sense that, on the largest scales, parallel lines stay parallel, the angles of triangles add up to 180 degrees, and the geometry obeys the rules of ordinary Euclidean space. The Planck data, combined with other measurements, gives us a value of omega k that is essentially indistinguishable from 0. The error bars on the measurement are tight. The universe is flat to within about 0.5%. That is an astonishing thing. It means that out to the largest scales we can measure, the geometry of the universe is, as far as we can tell, the same flat geometry your high school geometry teacher was talking about. The triangles work. The lines work. The Pythagorean theorem applies. On the scale of the entire observable cosmos. Now, flat geometry has consequences. A flat universe is, geometrically, either infinite or it has some kind of weird wraparound topology. Those are basically the 2 options. If the universe is genuinely flat and has the simplest possible topology, then it extends infinitely in every direction. There is just always more universe. You could travel for 10 billion years and find more galaxies. You could travel for 1 trillion years and find more galaxies. You could travel forever and there would always be more. The infinite plane that started infinite at the Big Bang and stretched ever since. But there is another option, and it is genuinely strange. The universe could be flat but finite, with a topology that wraps around on itself. Imagine the old video games where you walked off the right edge of the screen and reappeared on the left edge. Imagine that, but in 3 dimensions. The universe could be a kind of 3-dimensional torus, where if you flew far enough in any direction, you would eventually come back to your starting point, having gone all the way around without ever turning. The geometry would be flat the whole time. You would never feel any curvature. You would never sense an edge. There would be no edge. The space would just connect back to itself in a way that you could not perceive locally. This is what is meant by finite but unbounded. Finite in the sense that the total volume of the universe would be a number you could write down. Unbounded in the sense that there is no edge anywhere. You could not run into the boundary because there is no boundary. The space simply loops, and the crucial thing is that even in this finite version, the universe is still not expanding into anything. The wraparound topology is a property of the space itself. There is no exterior that the loop is set inside. The space just connects to itself internally without any reference to an outside. Whether the universe is infinite or whether it is a finite wraparound, the answer to the question, what is it expanding into, is exactly the same. Nothing. There is no into. Right now, we cannot tell which of these options is correct. The observable universe is enormous, but it is still finite, and a finite observation cannot rule out a wraparound that happens on scales larger than what we can see. If the universe loops back on itself only after, say, several 100 billion light-years, we would have no way of detecting it from where we sit. We would just see what looks like an infinite cosmos in every direction, identical to what we see now. Cosmologists have looked for telltale signs of wraparound, like repeating patterns in the cosmic microwave background, but they have not found any conclusive evidence. So, as far as the data is concerned, the universe might be infinite, or it might be incredibly large, or it might be finite with a wraparound on scales we cannot probe. All three are consistent with what we have measured. There is something philosophically jarring about this. It means that one of the most basic questions you could ask about the universe, namely, is it finite or infinite, may simply be undecidable from inside it. We may never be able to tell, even in principle. And that should give you a strange feeling, because it suggests that there are facts about the universe that are real, that are determined, that are either yes or no, and that we have no way of accessing. The universe knows whether it is finite or infinite. We do not, and we may never. But notice what both options share. In both cases, the universe has no exterior. In both cases, the expansion is not happening into anything. In both cases, the metric is just stretching. Internal distances are just growing, and there is no outside arena that any of this is occurring inside of. Whether the universe is infinite or whether it is a finite wraparound, the answer to the central question is the same. There is no into. There never was an into. The structure of the geometry simply does not include one. This is the moment, by the way, when the original question finally stops being a question and starts being a kind of fossil. It is something humans ask because of how human brains work, not because the universe has the structure that makes the question meaningful. We ask it because we evolved on a planet where every container had an outside. We ask it because we have never, in our entire evolutionary history, encountered a self-contained geometry. Our intuitions are calibrated for boxes and rooms and oceans and skies. They are not calibrated for the actual cosmos. So we have replaced the picture of expansion into something with the picture of internal growth in a self-contained geometry. We have replaced the picture of a center with the picture of every point being equivalent. We have replaced the picture of a finite edge with the picture of either an infinite expanse or a topological wraparound. And we have done this without ever leaving the firm ground of measurable, testable physics. None of this is speculation. All of this is what falls out of the equations when you take general relativity seriously and feed it the data from telescopes and satellites. But there is something we have not yet talked about, something that creates one of the most persistent misconceptions about the universe. There is a thing called the observable universe, and people tend to confuse it with the universe itself. And as we are about to see, the observable universe is not an edge. It is a kind of fog. And what that fog tells us, when you look at it carefully, is even stranger than what we have already discovered. Part 6. The observable trap. When astronomers talk about the observable universe, they are talking about a sphere with a radius of roughly 46.5 billion light-years centered on us. That number trips up almost everyone the first time they hear it, and for an extremely good reason. The universe is only about 13.8 billion years old. So, how can the observable universe extend 46 billion light-years in every direction? Wouldn't the maximum distance light could have travelled in that time be 13.8 billion light-years? Where did the extra 30 plus billion light-years come from? The answer is, of course, the expansion. When light left a distant galaxy 13 billion years ago, that galaxy was much closer to us than it is now. The light has been travelling toward us all that time, but during that travel, the space between us and the source has been stretching. The light kept going, the source kept getting further away, and now, when the light finally arrives at our telescopes, the original source is sitting at a present-day distance of roughly 46 billion light-years. The light's journey took 13 billion years. The current distance to where it came from is much greater. Both numbers are correct, they just describe different things. One is the time the light spent in transit, the other is the present distance to the source, after all the expansion that has happened during the trip. So the observable universe is not the universe. It is the part of the universe whose light has had time to reach us since the early universe became transparent. Beyond the observable universe, there is more universe. There are galaxies whose light has not yet had time to reach us. There are regions whose light may never reach us at all. The boundary of the observable universe is not the edge of reality. It is the edge of what we, sitting on this particular planet at this particular moment, can see. And this matters because people often picture the observable universe as a kind of rind, with the universe inside the rind being all there is. That picture is wrong. The observable universe is the inside of a fog. We are sitting at the center of a sphere of fog, and the boundary of that sphere is just the limit of how far light has had time to travel. Beyond that boundary, the fog continues. There is more space, more galaxies, more cosmos, and we have no access to it. Not because there is anything different about the geometry there, but because the light from those regions has not yet had time to make the journey, and in some cases, never will. When astronomers count the galaxies inside the observable universe, the current best estimate is roughly 2 trillion galaxies, each one containing, on average, somewhere between 100 million and 100 billion stars. The numbers get unwieldy quickly. If you tried to count every star in the observable universe at 1 star per second, you would die. Your civilization would die. The sun would die. The earth would have been swallowed by the swelling red sun and turned into a glowing cinder, and you would still not be done counting. And that is just the observable part. The actual universe, however large it is, contains far more than what we can see. The boundary of what we can see, by the way, has a specific physical origin. About 380,000 years after the Big Bang, the universe had cooled down enough that the soup of charged particles, electrons and protons, could settle into neutral hydrogen atoms. Before this happened, the universe was opaque. Photons could not travel any meaningful distance without scattering off free electrons. The whole universe was a glowing, foggy plasma. When neutralization happened, suddenly the photons were free. They could fly, and they have been flying ever since, for 13.8 billion years, slowly cooling as the metrics stretch their wavelengths into the microwave range. Those photons are the cosmic microwave background, and the surface from which they last scattered, the place in the sky where they last bounced off something before becoming free, is called the surface of last scattering. That surface is, in a sense, the practical edge of the observable universe. It is the furthest back in time we can directly see using light. We cannot see further because before that point, the universe was not transparent. It was a wall of glowing plasma. So when we look at the cosmic microwave background, we are not looking at the edge of the universe. We are looking at the limit of how far back in time light can take us. We are looking at the inside surface of a fog that surrounds us in every direction. The fog is not a wall. The fog is not a boundary. There is universe beyond the fog. We just cannot see it because the photons from beyond it could not reach us through the early plasma. There is something almost vertiginous about this. We are not sitting at the center of the universe in any meaningful sense. We are sitting at the center of a sphere of observation, a sphere defined by where we are and how long light has had to travel. Every observer everywhere has their own sphere. From a planet in a galaxy 10 billion light-years from here, that observer would see a different observable universe, partially overlapping with ours, partially not. Their sphere would extend in directions where ours could not see, and ours would extend in directions where theirs could not. There is no single observable universe. There is an observable universe per observer. And this is where the observable trap really bites. People hear 46.5 billion light-years and assume that is the size of the universe. It is not. It is the size of one particular observer's window onto the universe. The actual universe is bigger, much bigger, possibly infinitely bigger. We just cannot see all of it. The reason this matters for the central question is simple. The observable universe is not an edge. The boundary of what we can see is not the boundary of reality. So even if you tried to repurpose the observable universe as a kind of finite container, you would be making a category error. The container is not real. It is a personal limitation of our viewpoint. The cosmos extends beyond it, and nothing in the geometry beyond the observable region looks any different from the geometry inside it. There is no transition. There is no membrane. There is just more space, more galaxies, more of the same self-contained, expanding fabric going on for as far as the universe extends, which may be infinitely far. So now we have stripped the question of yet another assumption. The boundary you might have been picturing, even subconsciously, the apparent edge of what we can see, is not a real edge, it is a fog. And the fog has nothing to do with the question of what the universe is expanding into, because the fog is not the limit of the universe, it is just the limit of our view. But while we have been talking about how the universe is structured, we have been quietly assuming the expansion is just chugging along at a steady rate. It is not. Something has been done to the rate of expansion in the last few billion years that nobody saw coming, and when we discovered it, it changed cosmology forever. Part 7. The expansion is speeding up. In 1998, two competing teams of astronomers, working independently, announced one of the most surprising discoveries in the history of science. The teams were led by Adam Rees and Saul Perlmutter, with significant contributions from Brian Schmidt, and they had been doing what sounded like fairly routine work. They had been measuring the brightness of a particular kind of exploding star called a Type 1a supernova in galaxies at various distances across the universe. The goal was to map out how the expansion of the universe had behaved over cosmic time. The expectation was that the expansion should be slowing down. After all, gravity is attractive. All the matter in the universe pulls on all the other matter. So the natural picture was that the early expansion, kicked off by the Big Bang, should be gradually decelerating as gravity put on the brakes. Type 1a supernovae are useful for this kind of measurement because they are what astronomers call standard candles. They occur when a white dwarf star in a binary system accretes enough material from its companion to cross a critical mass threshold, at which point it detonates in a thermonuclear explosion of remarkably consistent brightness. Different Type 1a explosions have different absolute magnitudes, but the variations are small and predictable, which means if you know how bright one looks from here, you can work out how far away it is, because you know how bright it actually is. They are cosmic mile markers. When Rees, Perlmutter, and their teams started measuring distant Type 1a supernovae and comparing their brightnesses to what the deceleration model predicted, they found something wrong. The supernovae were too dim. They were further away than they should have been if the expansion had been slowing down all this time. The math, when worked out carefully, did not just disagree with deceleration, it went the other way. The expansion was not slowing down. It was speeding up. It had been speeding up for billions of years. Something was actively pushing the universe apart, and that something was overpowering the gravitational pull of all the matter in the cosmos. This was such an unexpected finding that the teams went over their data again and again trying to find the mistake. There was no mistake. Both teams independently arrived at the same conclusion. The expansion of the universe is accelerating, and whatever is causing the acceleration, it makes up the majority of the energy content of the cosmos, about 68% by current estimates. The remaining 32% is divided between ordinary matter and so-called dark matter, which is a separate mystery. But the big new entry in the cosmic ledger was this accelerating component. Cosmologists called it dark energy, mostly because that is a great way to describe something you have no idea about. The name is honest. We do not know what it is, we just know what it does. Now, I want to slow down here because it is easy to lose the thread when something this strange comes up, and I want to make sure we keep pulling on the same string. The acceleration of the universe is not, in the picture we have been building, the universe pushing harder into something. It is not the universe colonizing some external void at a higher rate. It is the metric of space itself stretching more rapidly. The same self-contained geometry we have been talking about, the same internal expansion with no outside, is now stretching faster and faster as time goes on. The change is in the rate at which distances grow. It is not a change in what the universe is expanding into, because there is still no into. It is a change in how the universe is expanding in itself, by itself, all over itself, at every point at once. Whatever dark energy is, it acts like a kind of pressure that pushes space apart. The simplest model treats it as a cosmological constant, a fixed energy density that is the same at every point in space and at every moment in time, which produces an accelerating expansion through general relativity. In this picture, dark energy is just a property of empty space itself. Every cubic meter of vacuum has a tiny amount of energy in it, and that energy drives the metric to stretch. As the universe expands, and there is more vacuum, there is more dark energy, which drives more expansion, which produces more vacuum, and so on. The acceleration is built into the geometry. But the cosmological constant is not the only possibility. Dark energy might be something more dynamic, something that changes over time. In recent years, results from instruments like the Dark Energy Spectroscopic Instrument, often abbreviated as DESI, have hinted that dark energy may not be perfectly constant after all. The data is preliminary and the interpretations are still being debated. But if the hints hold up, it would mean that the expansion rate is not just accelerating in a fixed way, but evolving in a more complex pattern. Dark energy might have been stronger or weaker in the past. It might be changing now. It might do strange things in the future. This matters for the central question, because it tells you that the geometry of the universe is not just stretching in a simple, predictable way. The geometry has its own dynamics, its own behavior, its own history. The expansion is not a passive process. It is a property of space that itself has structure and evolution. And whatever that property is, it is happening from inside the geometry. It is not being driven by anything outside. There is no outside agent pushing harder on the universe. The acceleration is internal. The universe is expanding faster because of something the geometry itself is doing. This brings us back, sharply, to the central thread. The question of what the universe is expanding into is not just unanswered. It is not just dissolved by the geometry. It is also unaffected by the acceleration. Whether the expansion is steady, slowing down, or speeding up, the answer to the original question is the same. There is no into. The acceleration just changes the rate at which the internal stretching happens. It does not introduce an outside. It does not summon a container. It does not give the universe somewhere new to go. The geometry is still self-contained. The change is happening within the system, not at its boundary, because there is no boundary. But the acceleration does have consequences, and one of those consequences is that the universe, in a very real sense, is starting to leave us. As space stretches faster and faster, more and more of the cosmos is being carried out of our reach. There are galaxies right now whose light is currently traveling toward us, and which, due to the accelerating expansion, will never arrive. The space between us and them is growing faster than the light can cross it. They are not just receding. They are slipping past the boundary of what we can ever access in any way ever. They are crossing what cosmologists call the cosmological event horizon, and the existence of that horizon is one of the strangest, loneliest facts in all of physics. Part 8. The horizon that erases reality. The cosmological event horizon sits, right now, at a distance of about 16 to 17 billion light-years from us. That number might sound similar to the size of the observable universe, but it is doing a different job, and the difference matters enormously. The observable universe is defined by where light has had time to come from since the early universe became transparent. The cosmological event horizon is defined by where light emitted right now will ever be able to reach us, given the future expansion of the universe. They are two different boundaries, defined by two different physical processes, and they have very different implications. The observable universe tells you what you can see. The event horizon tells you what you can ever see, including in the future. Anything beyond the event horizon, right now, is gone. Not in the sense that it has stopped existing. Not in the sense that it has fallen apart. The galaxies out there are still real. They are still doing what galaxies do, with their stars and their planets, and presumably whatever else is going on out there. But because the space between us and them is stretching fast enough, the photons they emit today will never close the gap. The light will travel, and the gap will keep widening, faster than the light can cross it, and the photons will fall behind forever. The galaxies are causally disconnected from us. They might as well not exist from our perspective. We will never see them again. We will never receive any signal from them. They are gone, even though they are still there. This is happening right now, in real time, as you sit watching this. There is a horizon out there, 16 plus billion light years away, and galaxies are crossing it constantly. Every second, a new patch of the universe slides over the threshold, leaves the region we can ever access, and joins the silent majority of the cosmos that is permanently severed from us. We are losing the universe, not by motion, not by destruction, but by geometry. The expansion is taking it from us, smoothly and quietly and without any drama, and there is nothing we can ever do about it. I want to bring this back to the central thread before going further, because this is the kind of fact that can pull you off into existential territory if you are not careful, and we are still trying to understand what the universe is expanding into. The horizon I just described is a feature of the geometry. It is not an edge of the universe. It is not a wall. It is not something out there in the cosmos that the expansion is bumping into. The horizon is, in essence, a consequence of how the metric is changing over time. It exists because the rate of expansion is high enough, and because the universe has the structure it has, that some regions are now causally separated from us forever. The horizon is internal to the geometry. It is not a boundary in any external space. It is a property of the relationship between us and other regions, defined entirely within the self-contained system we have been talking about. If you were a different observer, somewhere else in the universe, you would have your own event horizon. It would be in a different place. Some of the regions that are inside our event horizon would be outside theirs. Some of the regions that are outside ours would be inside theirs. There is no single event horizon for the universe as a whole. There is one per observer, just like there is one observable universe per observer. The cosmos, from the outside, has no edges. From any inside vantage point, the geometry creates these personal horizons, these limits to what each observer can ever access. So when you hear that galaxies are slipping past our event horizon, you should not picture them flying off the edge of the universe. They are not flying anywhere in the local sense. They are just being carried by the metric expansion to greater and greater distances from us. And the rate of that carrying is exceeding the speed of light, which means their light cannot get back to us. They are, in their own neighborhoods, sitting still. Their stars are still burning. Their planets, if they have any, are still spinning. From their perspective, nothing has happened. They have not crossed any boundary. They are not inside any kind of trapped region. They are just there, doing their thing. It is only from our perspective, with our particular location and our particular metric history, that they have effectively vanished. This is what cosmologists mean by causal disconnection. The galaxy and us are no longer in causal contact. No information can pass between us. No light, no particles, no gravitational waves, no signals of any kind. The space between us is growing faster than any messenger could cross it. We are, in the most literal sense available, isolated from them. They might as well be in a different universe. And the strangest thing about this is that it is happening continuously. The horizon is not stationary. The horizon is, in our universe, slowly but steadily sweeping inward in terms of which galaxies are inside it, even though the horizon itself is at a roughly fixed distance. As space stretches, distant galaxies cross the threshold one by one, leaving the accessible region. The set of galaxies we will ever be able to influence or hear from is shrinking, day by day, year by year, eon by eon. We are watching, in a sense, the gradual erasure of our cosmic context. The universe, from our point of view, is getting smaller in terms of what we can ever interact with, even as the universe as a whole gets bigger. This is, again, not the universe expanding into something. This is the universe expanding within itself in a way that creates these horizons. The horizons emerge from the geometry. The geometry has no outside. The horizon is not a wall around the cosmos. It is a feature of the self-contained metric, a feature that exists because the metric is doing what it is doing. The expansion is internal. The consequences of the expansion are internal. The fact that we are losing the universe is internal. None of this requires an external space, an external container, or any kind of into. But once you see that this is happening, you cannot help but ask the next question. What does this look like, projected far enough into the future? What happens to the universe, from our point of view, if the expansion just keeps going? If the horizon keeps doing its work, if the galaxies keep crossing, if the metric keeps stretching, what is left at the end? What does the cosmos look like to any observer that lives long enough to watch it happen? Part 9. The end of the visible universe. Project the current cosmological model forward by about 100 billion years, and the picture changes dramatically. 100 billion years is, by the standards of cosmic time, not actually that long. The universe is currently 13.8 billion years old. 100 billion years is roughly 7 times the current age. That sounds like a lot. By human standards, it is a lot. But for the universe, it is a relatively modest extrapolation. And in that span of time, if the current cosmological model is correct, almost every galaxy we can currently see in the sky will have crossed our event horizon and become permanently invisible to us. This is not the end of the universe. The universe will keep going. What ends in this projection is the era during which observers in our cosmic neighborhood can see the rest of the cosmos. By 100 billion years from now, the only galaxies we will be able to see from a future Milky Way descendant, or whatever survives in our local area, are the galaxies of our own gravitationally bound group. The local group, which includes the Milky Way, Andromeda, the Triangulum Galaxy, and a handful of smaller satellite galaxies, is held together by mutual gravitational attraction. That gravitational attraction is, locally, much stronger than the cosmological expansion. So the local group, despite the expansion of the universe, is not pulling apart. In fact, the Milky Way and Andromeda are currently moving toward each other and will probably merge into a single galaxy in roughly 4 to 5 billion years, long before the 100 billion year horizon I am describing. So, 100 billion years from now, our region of the cosmos will likely look like one big merged galaxy, formed from the ancient remnants of the Milky Way and Andromeda and whatever else got pulled in along the way, sitting alone in the middle of an apparently empty cosmos. There will be no other galaxies visible. They will have all crossed the event horizon. The cosmic microwave background, that ancient glow we currently use to study the early universe, will have been redshifted into invisibility. The wavelengths will have been stretched so much that the photons will be too low in energy and too sparse in number to detect. The cosmic microwave background will, for all practical purposes, be gone. Not destroyed, just stretched beyond detection. Imagine being an astronomer in that era. Imagine being on a planet orbiting a long dead star in the merged galactic remnant of the Milky Way and Andromeda, looking out into the night sky. You would see your own galaxy. You would see the stars within it. You would see whatever is left of the star formation in your local neighborhood, although by 100 billion years from now, most of the gas will have been used up, and most of the stars will be small, dim, long-lived red dwarfs sliding into eventual death. Beyond the galaxy, you would see nothing, just blackness. No other galaxies visible, no cosmic background, no evidence anywhere that there was ever such a thing as a Big Bang or an expanding cosmos. If those future astronomers tried to do cosmology, they would arrive at a completely different model than ours. They would see a single, isolated galaxy in an apparently static, empty universe. They would have no evidence of expansion. They would have no evidence of any other galaxies. They would have no cosmic microwave background to study. The clues we use today to piece together the history of the cosmos would be gone, redshifted away, or carried over the horizon. They would, almost certainly, conclude that they live in a single, eternal, unchanging galaxy in a vast, empty void, and they would be wrong. There is no one out there to tell them they are wrong. There is no record outside their galaxy that says, look, here is the actual history of the cosmos, here is what really happened. The history is, from their perspective, gone. This is one of the most haunting facts in cosmology. The universe is in a unique window right now. We happen to live in an era when we can still see the early universe. We can still see the cosmic microwave background. We can still see distant galaxies. We can still piece together a coherent history of the cosmos. Future observers, just a few orders of magnitude into the future, will not be able to do any of this. The information will be gone. The universe will have, in a real sense, erased its own history from the perspective of any future observer. We are not just early. We are uniquely situated. Our era is one in which the evidence is still here. The era after ours, stretching for an essentially unlimited amount of cosmic time, will be one in which the evidence is no longer accessible. If you were going to study the universe, this is the moment to do it. Not later, not earlier. Right now is the window. And the window is closing. Bringing this back to the central thread, none of this is the universe disappearing into anything. None of the galaxies that are crossing the event horizon are going somewhere else. They are not entering a void. They are not leaving the cosmos for some external arena. They are simply being carried by the metric expansion to distances from us that exceed what light can ever traverse, given how fast the expansion is. The disappearance is not into. The disappearance is, again, internal. It is a feature of the geometry of the universe, a consequence of how space stretches over time. The universe is not losing pieces of itself to some external place. The universe is just spreading out, in itself by itself in a way that makes more and more of itself inaccessible to any given observer. So we have, at this point, a fairly developed picture. The universe is a self-contained geometry with no edge and no exterior, expanding internally in a way that involves the metric itself, stretching, doing it at an accelerating rate due to dark energy, creating event horizons that are causally separating us from more and more of the cosmos, and projecting forward. This process will eventually erase almost all evidence of the rest of the universe from any given observer's view. But this is the standard model. This is, more or less, the cleanest version of the story we can currently tell. And it works, in the sense that it fits a vast amount of data. But there are problems. There are pieces that do not fit. There are anomalies that suggest, however gently, that we do not yet have the whole picture. The model, in its current form, may be breaking, and the cracks in the model are themselves part of the answer to the central question. Part 10. The Hubble Tension. The Hubble constant, named after the same Edwin Hubble we met earlier, is the number that tells you how fast the universe is expanding right now. It is, in essence, the local rate at which galaxies are receding per unit distance. The way you would measure it is, in principle, simple. You measure the distance to a bunch of galaxies. You measure how fast they are receding. You divide one by the other. You get a number with units of kilometers per second per megaparsec, which sounds wonky but just means a velocity per distance. The current value is somewhere in the neighborhood of 70 kilometers per second per megaparsec, give or take, and that range is where the trouble starts. There are two main ways to measure the Hubble constant. The first uses the early universe. You take the cosmic microwave background, the leftover radiation from when the universe was 380,000 years old, and you analyze it carefully. The pattern of fluctuations in the cosmic microwave background, combined with the standard cosmological model, predicts a specific value for the Hubble constant today. When the Planck satellite did this analysis, it came up with a number around 67 kilometers per second per megaparsec. The second way uses the late universe. You use type 1a supernovae, those standard candles we talked about, in nearby galaxies, calibrated using stars whose distances you can measure directly. You measure their recession velocities and their distances, and you compute the Hubble constant directly from those data. When this method has been carried out by Adam Rees and his collaborators, using data from the Hubble Space Telescope and now the James Webb Space Telescope, the answer comes out around 73 kilometers per second per megaparsec. Those numbers are not the same. The difference between 67 and 73 sounds small, but the error bars on both measurements are tight, and the discrepancy is statistically significant. We are talking about a disagreement at roughly 5 sigma, which means the probability that it is just statistical noise is essentially zero. Something real is going on. The two methods, both of which should give the same answer in principle, are giving different answers. This is what cosmologists call the Hubble tension, and it has been the most persistent, unresolved problem in cosmology for years. There are several possible explanations. The first is that one of the measurements is wrong, due to some systematic error nobody has yet identified. This is possible, but increasingly unlikely, as the measurements have been redone with newer instruments and the discrepancy has not gone away. The second is that the cosmological model itself is incomplete. There may be new physics, something we do not yet know about, that affects the early universe differently from the late universe and explains the discrepancy. Possibilities include extra forms of energy, new particles, modifications to dark energy, or other exotic ingredients. None of these have yet been confirmed. What this tells us, brought back to the central thread, is that even the rate at which the universe is expanding is not fully understood. We know expansion is happening. We have 1,000 independent lines of evidence for it. But the actual numerical rate, the basic parameter that describes how fast the metric is stretching, is in dispute. The two methods that should agree do not agree. Something about our model of space is off, and we have not yet figured out what. So even the fundamental quantity that describes the internal evolution of the geometry, the parameter that determines how much the metric is changing per unit time, is not yet pinned down. The expansion is real. The expansion is not entirely understood. And the fact that it is not entirely understood is one more reason to be cautious about claims, including claims about what the universe is or is not expanding into. Part 11. The worst prediction in physics. There is another problem with our model of space, and this one is, by some accounts, the largest theoretical mismatch in the history of physics. It involves the energy of the vacuum. In quantum field theory, the framework that underlies particle physics, empty space is not actually empty. The vacuum is a seething bath of fluctuations, where particles and antiparticles flicker in and out of existence on time scales too short to directly observe. These fluctuations are real. We have measured their effects in laboratories. They cause subtle shifts in atomic energy levels. They cause attractive forces between metal plates placed close together. The vacuum is not nothing. The vacuum has structure. The vacuum has energy. If you try to calculate, from quantum field theory, how much energy the vacuum should have per unit volume, you get an enormous number. The exact value depends on what cutoffs you use, but it ends up something on the order of 10 to the 72nd power kilograms per cubic meter, or thereabouts. That is a stupendous density. It is so huge that if it were real, the universe would have ripped itself apart in the first instant of its existence. The geometry would have stretched at such an absurd rate that nothing could form. Now, compare this to what we actually observe. We see a universe with a small but non-zero acceleration of expansion, driven by something that behaves like vacuum energy. We can measure the energy density of this dark energy from cosmological observations. The number we get is tiny, about 10 to the negative 27th kilograms per cubic meter. Tiny, almost imperceptible, just enough to drive the slow, accelerating expansion we observe over billions of years. The mismatch between the quantum field theory prediction and the observed value is, depending on how you calculate it, around a factor of 10 to the 120th. That is a 1 followed by 120 zeros. It is the largest known disagreement between a theoretical prediction and an experimental measurement in the history of science. The vacuum energy is, by quantum field theory, supposed to be 10 to the 120th times what it actually is. By any reasonable standard, this means our theory is profoundly wrong about something fundamental. Either quantum field theory is dramatically misapplied here, or general relativity is not the whole story, or there is some deep cancellation we do not understand, or all of the above. What this means for our central thread is that the energy of space, the actual stuff that makes up the fabric we have been talking about, is something we do not understand. Space is not empty. Space has energy. Space has structure. The expansion of space is driven, at least in part, by this energy. But we do not actually know what this energy is, where it comes from, why it has the value it does, or how it relates to the rest of physics. The thing that is doing the expanding is, at a basic level, mysterious to us. So when we say the universe is expanding, we are using a word, expanding, whose underlying mechanism we cannot fully account for. There is an internal consistency problem in our model of space, and that problem hangs over every conversation about what space is and what is happening to it. So we have built a picture of the universe as a self-contained geometry, with no edge and no exterior, expanding from within, accelerating, creating horizons, projecting toward a future of cosmic isolation, with the rate of expansion in dispute and the energy of space itself off by a factor of 10 to the 120th from theoretical prediction. This is, to put it mildly, not a finished theory. The original question about what the universe is expanding into was malformed. The answers we have arrived at instead are, themselves, deeply incomplete. And before we go further, there is one more class of ideas we should address, because they show up constantly in conversations about cosmology, and they tend to feel like they are answering the central question even when they are not. Part 12. Is there actually an outside? When people first hear that the universe has no outside, a natural follow-up is to ask about multiverses. Is our universe maybe one of many? Could there be other universes outside ours? Other regions of reality beyond what we can see? Could the something that the universe is expanding into be other universes, or some kind of larger meta-cosmos that contains all the universes? These questions lie, mostly, in the realm of theoretical speculation, but they are not idle. There are serious physicists who have proposed serious models in which something like a multiverse exists. The most well-known is the eternal inflation picture, developed initially by Alan Guth in the early 1980s and extended by Andre Linde and others. Inflation is a proposed brief period of extremely rapid expansion in the very early universe, occurring in something like 10 to the negative 35th seconds, during which the universe stretched by a factor of at least 10 to the 26th or so. Inflation explains a number of features of the observed universe, like why it is so flat and why the cosmic microwave background is so smooth. There is good observational evidence that something like inflation happened. The exact details are still being worked out. In the eternal inflation picture, inflation does not stop everywhere at the same time. Most of the inflating region keeps inflating at exponentially increasing rates, while small bubbles within it stop inflating and become regions like our observable universe. Each bubble is, in this picture, a kind of universe in itself. The inflating background between the bubbles is so vast and so far-stretching that the bubbles never collide. They are causally disconnected from each other. Each bubble could have its own values of physical constants, its own physics, its own history. The whole structure, with the inflating background and the bubbles, is what gets called the multiverse. There are other versions. Some versions of string theory predict a vast number of possible vacuum states, each corresponding to a different kind of universe with different physics, and in some pictures, all of these vacua are realized somewhere in the larger reality. There are speculative ideas where every black hole in our universe contains the seed of a baby universe inside it, leading to a kind of cosmic genealogy. There are cyclic models where the universe goes through repeated bounces, with each cycle being a kind of universe. There are more exotic ideas involving higher dimensional structures called branes that can collide and produce universes. Now, I want to be careful here because these ideas are speculative. They are not currently supported by direct observational evidence. They emerge from the math of certain theoretical models, but those models themselves are not yet confirmed. The multiverse, in any of its forms, is a hypothesis, not an established fact. So, when you hear someone confidently tell you that there are infinitely many universes out there, they are speaking from a particular theoretical perspective, not from data. But suppose, for the sake of argument, that one of these multiverse pictures is correct. Suppose there really are other universes outside ours. Does that answer the question, what is our universe expanding into? Does it tell us that we have a container after all, that the void at the edge of our cosmos is filled with other cosmoses? The answer is, not really. Even if multiverse pictures are correct, they do not deliver the kind of answer the original question wants. In the eternal inflation picture, our universe is not expanding into the inflating background, because the inflating background was, in some sense, the parent of our universe, the region from which our bubble nucleated. We are not pushing into it. We are inside it, in a manner of speaking, but the geometry is such that we cannot reach the rest of it. The boundary between our bubble and the inflating background is not a wall we are pushing against. It is a region of different physics, and we cannot get there. More importantly, even if there are other universes out there, the question just relocates. If our universe is expanding within a multiverse, what is the multiverse doing? Is the multiverse expanding? If so, into what? If not, why not? Is the multiverse the final container, the truly outside thing, the actual edge of reality? Or is the multiverse itself inside something else, some meta-multiverse, and so on, an infinite regress of containers? At every level, the original question reappears. You can always ask, what is the largest thing expanding into? And at every level, you either accept that there is no into, that the geometry is self-contained, or you posit another level of containment, which just kicks the can. This is one of the deepest features of the central question. It does not get answered by adding more containers. It gets dissolved only by recognizing that geometries can be self-contained, that expansion can be internal, that the universe does not need an exterior to make sense. Multiverses do not save you from this. They just delay the moment when you have to face it. So even if our universe is one of many, the same answer applies. The whole structure, whatever it is, however many levels of containment it has, eventually has to be self-contained. There is no infinite regress that lets you avoid it. At some point, the largest thing, whatever it is what it is, with no exterior. The question of what it is expanding into, if it is expanding, has the same answer as the question of what our universe is expanding into. Nothing. There is no into. There never was. And no amount of additional cosmos in the picture changes that. So we have, in a sense, gone as far as we can with the picture of space as a fundamental thing. We have explored its geometry, its expansion, its horizons, its acceleration, the cracks in our model, the speculative possibilities for what might lie beyond it. And, at every step, the original question has been deepened or dissolved, but never answered in the way it wanted. There is no into, the universe is self-contained, the geometry is what it is, end of story. Except, there is a possibility we have not yet examined, and it is the strangest one of all. It is the possibility that space itself is not fundamental, that the geometry we have been talking about is not the bottom layer of reality, that there is something beneath the metric, something more basic, something that the metric emerges from, the way temperature emerges from molecules. If that is true, then the question, what is the universe expanding into, becomes not just unanswerable, but unaskable, because the thing it is asking about is not the thing reality is actually made of. Part 13. Space is not fundamental. In 1997, an Argentine physicist named Juan Maldacena, then working at Harvard, published a paper that quietly changed the foundations of theoretical physics. The paper was about a relationship between two very different-looking theories. One was a theory of gravity in a particular kind of space-time called anti-de Sitter space, a five-dimensional, curved geometry with some specific mathematical properties. The other was a quantum field theory living on the four-dimensional boundary of that space-time with no gravity at all, just particles and fields interacting on the surface. Maldacena's paper argued that these two theories, which look completely different, are actually equivalent. Anything you can describe in one, you can describe in the other. They are two different languages for the same physical content. This relationship is now called ADS, CFT correspondence, or the holographic principle in its broader form. The implications, when you sit with them, are staggering. What Maldacena showed is that gravity in a region of space can be fully encoded by a theory living on the boundary of that region with one fewer dimension. The interior space, with all its gravitational dynamics, all its bending and stretching, all its black holes and gravitational waves, is somehow secretly contained in the information sitting on the lower dimensional surface that wraps it. The volume is described by the boundary. The three-dimensional space in this picture is something like a hologram, a projection of information stored on a two-dimensional surface. Now, our universe is not anti-de Sitter space. Our universe is more complicated than that, with its own particular geometry and matter content, and the precise form of holography that applies to it, if any, is still under investigation. But the idea has been deeply influential, and it has led to a whole series of investigations into whether space, in general, is fundamental, or whether it might be an emergent feature of something deeper. Here is what emergence means, in case the word is fuzzy. In physics, some properties are fundamental in the sense that they are the basic ingredients of a theory. Other properties are emergent in the sense that they arise from the collective behavior of more basic things. Temperature is emergent. There is no temperature of a single molecule. Temperature is what you get when you have many molecules and you describe their average kinetic energy. It is real. It has consequences. It is not a fiction. But it is not at the bottom layer of reality. The bottom layer is the molecules. Temperature is what the molecules look like when you zoom out. Holography, and a lot of subsequent work, has raised the possibility that space is like temperature. That space is not at the bottom layer of reality, that there are more basic ingredients, things that are not themselves spatial, and that what we call space is what those ingredients look like when you zoom out. If that is right, then the geometry we have been talking about, the metric, the expansion, the horizons, all of it, is a kind of statistical or coarse-grained description of something more fundamental. The bottom layer is not space. Space is what the bottom layer organizes itself into. What is the bottom layer then? The strongest current candidate, and this is where the story gets really wild, is quantum entanglement. I am going to take a moment to say what entanglement is, because it is the kind of word that gets thrown around and it deserves a careful description. Entanglement is a property of quantum systems where two or more particles become correlated in a way that cannot be explained by any local description. If you have two entangled particles, separated by any distance, measuring one of them instantaneously determines what you would find when you measure the other. This is not because there is a signal traveling between them. There is no signal. It is because the two particles are not really two separate objects. They are parts of a single quantum state that extends across both of them. Entanglement is the most quantum thing about quantum mechanics. It is what makes quantum reality genuinely different from classical reality. For most of the 20th century, entanglement was treated as a curious feature of quantum mechanics, useful for exotic experiments, but not particularly relevant to the fundamental structure of space and time. That has changed. Over the last roughly 20 years, a series of physicists, most prominently including Mark van Ramsdonk at the University of British Columbia, have developed an idea that, the more you sit with it, the more it changes how you think about the cosmos. The idea is that space, the geometry we live in, is built out of entanglement. That the connections between regions of space, the very fact that two nearby points are nearby and not far apart, is a manifestation of quantum entanglement between the degrees of freedom that live in those regions. Disentangle the regions, and the space between them falls apart. Entangle them more, and they pull closer. Space, in this picture, is a kind of geometric expression of entanglement structure. Van Ramsdonk demonstrated this in the context of holography with a striking thought experiment. He showed that if you take a holographic space-time and gradually reduce the entanglement between the two halves of the boundary theory, the corresponding geometry in the interior gets pinched off, with the two halves of space becoming further and further apart until they are completely disconnected, like cutting a noodle. The geometry in the interior is held together by the entanglement on the boundary. Less entanglement means less geometry. No entanglement means no geometry at all. This picture has been deepened by an idea due to Leonard Susskind and Maldacena called ER equals EPR. The name is a kind of inside joke. ER refers to Einstein-Rosen bridges, which are the original mathematical solutions in general relativity that we now call wormholes. EPR refers to Einstein-Podolsky-Rosen pairs, which are the classic example of entangled particles. The idea is that these two things, geometric wormholes connecting separate regions of space and quantum entanglement between particles, are at some deep level the same phenomenon. Entanglement creates wormhole-like connections at the quantum level. Space is woven from these threads. What does any of this mean for the central question? It means that the geometry we have been talking about, the geometry of the universe with its expansion and its horizons and its accelerating metric, is not necessarily the bottom layer of reality. The bottom layer might be something more like a vast structure of quantum entanglement, with no spatial properties at all, and what we call space is what that structure looks like when you organize it appropriately. The expansion of the universe, in this picture, is not just the metric stretching, it is a change in the underlying entanglement structure that supports the metric. Whatever the metric is doing, there is something deeper that is doing it. The key consequence for our question is this: if space is emergent, then the question, what is the universe expanding into, is operating at the wrong level. It is asking about what space is doing relative to something else, but space is not the thing. Space is a description, a high-level pattern, a coarse-grained projection of something more fundamental. Asking what the universe is expanding into, in this framework, is like asking what the temperature is rising into. Temperature does not rise into anything. Temperature is what the molecules are doing. If the molecules speed up, temperature rises. There is no into, there is no container, there is only the underlying behavior of the more basic ingredients. Space, in the emergent picture, is the same. There is no into, there is only the underlying entanglement structure changing in a way that we describe on the surface as expansion. So if you have been waiting for the moment when the original question gets fully replaced rather than dissolved, this is it. We have moved from a picture in which space is fundamental and self-contained to a picture in which space is not fundamental at all. And in either case, the original question fails to have an answer. In the self-contained picture, there is no exterior. In the emergent picture, the question is about the wrong layer. Either way, there is no into. The question, as posed, simply does not match how reality is structured. But the entanglement picture, beautiful as it is, raises new questions. What exactly is the underlying structure? How does it produce something that looks like space? What does expansion correspond to at the deeper level? And how would we ever know? Because if the underlying reality is not spatial, our intuitions, which are built for space, are even less helpful than they were before. Part 14. Entanglement builds reality. To really sit with what the entanglement picture is telling us, you have to give up something even bigger than the idea of an outside. You have to give up the idea that space, in any classical sense, is real. Let me unpack what I mean by that, because this is one of those places where the words can mislead if we are not careful. When we say space is real, in everyday speech, we usually mean something like, there is a thing that exists, and it has dimensions, and objects live inside it. The thing that we call space is, in this picture, a kind of arena. It is a container. It is the stage on which physics happens. It has its own properties, like geometry and curvature, and those properties influence how matter and energy behave. The thing called space is, in this picture, something like a fundamental entity. It is not made of anything else. It is just there, baseline, primary, real. The emergent picture says, no, that is not what space is. Space is not a fundamental entity. Space is a description we give to a particular pattern of entanglement among more basic degrees of freedom, degrees of freedom that themselves do not have spatial properties. The space you live in, the three-dimensional volume that contains your kitchen and your car and your morning commute, is, at its most fundamental level, a vast and intricate web of quantum correlations. Two regions are close in space because the degrees of freedom in those regions are highly entangled with each other. Two regions are far apart because the degrees of freedom in them are weakly entangled. The geometry is not the basic thing, the entanglement is. The geometry is what you get when you summarize the entanglement structure in a particular geometric language. This is a radical shift, and it is genuinely hard to wrap your head around. The thing you have been calling space your whole life, the thing that feels so basic and obvious that questioning it seems absurd, may not actually be a thing. It may be a pattern in something else. And the something else is the actual reality. Now, I want to be careful about how strongly I claim this. The idea that space is emergent from entanglement is, at the moment, a leading research direction, not an established fact. There are concrete results, like Van Ramsdonk's work and the developments around ER equals EPR, that strongly support the idea in specific theoretical contexts, particularly in the holographic settings where the math is most under control. There are also significant open questions about how this picture extends to realistic cosmologies like ours. But the direction is real. The evidence is accumulating. The theoretical mathematics is increasingly aimed at the picture in which space is not fundamental but emergent. And whatever the final answer turns out to be, the fact that this is even a serious possibility tells us something important about how we should think about the original question. Let me try to make the entanglement picture concrete with a metaphor, knowing that all metaphors break, but hoping this one helps. Imagine a vast collection of dots. The dots have some quantum state. Some pairs of dots are highly entangled, meaning their states are tightly correlated. Some pairs are weakly entangled. Some are not entangled at all. Now imagine that you wanted to draw a picture of how strongly each pair of dots is correlated. You would put the highly entangled pairs close together on your picture because they are tightly linked. You would put the weakly entangled pairs far apart because they are loosely linked. The unentangled dots might be at infinite distance, in some sense, because they have nothing to do with each other. What you would have drawn, in the end, is a kind of geometry. The arrangement of the dots in your picture would form a shape. That shape is what the entanglement looks like when you visualize it spatially. The more entanglement, the more elaborate the geometry. The less entanglement, the simpler. In the limit, with the right kind of entanglement structure, you might get something that looks just like the three-dimensional geometry we live in. The dots would arrange into a smooth, continuous, three-dimensional space. The entanglement would be the glue. The space would be the picture. This is, very loosely, what the emergent picture is saying. Space is the picture. Entanglement is the glue. The dots, whatever they are the actual basic ingredients. The space we live in is what the glue looks like when there is a lot of it, structured in a particular way. Now apply this to expansion. If space is emergent from entanglement, then the expansion of the universe is not the metric stretching for its own sake. The expansion is what happens when the underlying entanglement structure changes in a particular way over time. The dots, in some sense, are slowly becoming less correlated with each other. The geometry, as a result, becomes one in which distances are growing. The expansion, in this picture, is a kind of slow disentanglement, a gradual loosening of the quantum correlations that hold the universe's geometry together. This is why the original question is so deeply malformed in this picture. Asking what the universe is expanding into is like asking what a melting ice cube is melting into. The melting is not motion of the ice cube into something else. The melting is the breakdown of the structure that made the ice cube an ice cube. The water molecules that used to be locked into a crystal lattice are now sliding around as a liquid. There is no into, there is just a change in the organization. The expansion of space in the entanglement picture is similar. It is a change in the structure that gives rise to space. It is not motion through anything. It is the rearrangement of the underlying ingredients in a way that, on the surface, looks like the geometry stretching. I want to bring all of this back to the central thread one more time, because it is easy to get lost in the strangeness of this picture. The question we started with, what is the universe expanding into, was a question about space and what space is moving into or growing into. Throughout this video, we have peeled back layer after layer of assumptions in that question. We have shown that the universe has no center. We have shown that it has no edge. We have shown that it is self-contained, that it does not need to be embedded in anything larger, that even multiverse hypotheses do not deliver the kind of into that the question wants. And now we are at the deepest layer we currently have access to, in which space itself may not be a fundamental thing, in which the geometry may emerge from quantum entanglement, in which the expansion may be a manifestation of changes in the underlying correlations. At every layer, the answer is the same. There is no into. The expansion is internal to the system, where internal might not even have a meaning at the deepest level, because the system might not have spatial structure at all. The original question is, in every framework we have explored, malformed. It assumes a structure of reality that the universe does not have. So now we are ready, at last, to come back to the question one more time, not to answer it. We cannot answer it, because, as we have seen, the question is not the right shape for the universe we live in. But we can ask it again, knowing what we know now, and watch what happens. Part 15. The question repeats, but it is different now. What is the universe expanding into? You have spent the last 2 hours hearing me deconstruct this question, layer by layer, and yet I want you to ask it one more time. I want you to ask it knowing everything we have just gone through, and I want you to notice how it sounds different now. Not because the words have changed, the words are the same, but because the assumptions that gave the words their meaning have been stripped away one by one, and what is left is something stranger. When you first asked the question, you were almost certainly assuming a container. You were imagining the universe as a thing inside a larger thing, a glowing ball in a black void, growing outward, taking up more and more of the void as it expanded. That assumption was wrong. There is no container. There is no void around the universe that the universe is filling up. The universe is not inside anything. It is the entire spatial extent of reality, by definition, and there is no surrounding arena in which it sits. When you asked the question, you were also assuming a boundary. You were picturing the universe as having an edge, somewhere out there, a place where the universe ends and the void begins. That assumption was wrong too. The universe has no edge. Whether it is infinite or finite with a wraparound topology, in either case, there is no boundary you could ever reach. You could travel forever in any direction, and you would only ever encounter more of the same self-contained geometry. There is no wall. There is no membrane. There is no place where the universe ends. When you asked the question, you were assuming an external space, some larger arena that contains all of this, some bigger geometry inside which our geometry sits. That assumption was wrong. The universe is not embedded in any larger space. The mathematics of general relativity describes geometries that are intrinsic, geometries that have shape and structure entirely from within, geometries that do not need any surrounding arena to be defined. Our universe is one of those. It is a self-contained geometry. It does not require any external space to make sense of it. And when you asked the question, you were assuming that space itself was a fundamental thing, the kind of thing that could be expanding into something or not. That assumption may also be wrong. Space, at the deepest level we currently have access to, may not be fundamental at all. It may emerge from quantum entanglement, from a more basic structure that has no spatial properties of its own. If that is right, then asking what space is expanding into is asking the wrong kind of question entirely. It is asking about what space is doing relative to something else, but space is a description, not a primary entity. The thing that is changing is not space. The thing that is changing is the underlying entanglement structure that gives rise to what we call space. So when you ask the question one more time, what is the universe expanding into? Here is what is actually happening. You are using a sentence that requires the universe to be the kind of thing that has a context, an exterior, a place to expand toward. The universe is not that kind of thing. The sentence does not have a referent. The grammar is intact. The meaning, when you push on it, falls apart. It is, in the end, like asking what is north of the North Pole. The words make a sentence, but the sentence does not point to anything real, because the geometry of the planet does not have a north of north. The geometry of the universe does not have an into. Now, I want to be careful here, because I do not want this to land as a dismissal. I do not want to leave you with the feeling that the question was stupid, or that you were silly for asking it. The question is not stupid. The question is the natural reflex of a brain that evolved on a planet, in a body, in a culture, where every container had an outside and every expansion happened inside something else. The question is the human mind doing exactly what it was built to do. It is just that the universe is not built for the question. The universe is built differently. And the work of cosmology, the slow accumulation of measurements and theories and reframings, is the work of catching up to that, of replacing our intuitive containers with something more accurate, of learning to speak the language of self-contained geometries and emergent spaces and internal expansions. Let me retrace the journey, because I want you to see how all the pieces come together. We started with Edwin Hubble in 1929, looking at the redshifts of distant galaxies and noticing that everything was receding, with the further objects receding faster. We moved to general relativity, where we saw that this expansion is not motion through space, but a change in the metric of space itself. We saw that the Big Bang did not happen at a place, but at every place, all at once, in a space that may already have been infinite. We saw that the universe is flat to within 0.5%, which means it is either infinite or finite with some kind of wraparound topology, but in either case has no edge. We saw that the observable universe is not the universe, just a sphere of fog defined by how far light has had time to travel. We saw that the expansion is accelerating, driven by a mysterious dark energy. We saw that this acceleration creates an event horizon, beyond which more and more of the cosmos is becoming permanently inaccessible. We saw that, projected forward, the universe will, from the perspective of any future observer, almost completely disappear, leaving only their local galaxy in apparent emptiness. We saw that even the rate of expansion is in dispute, with the Hubble tension hinting at unknown physics. We saw that the energy of space itself is off by a factor of 10 to the 120th from what theory predicts. We saw that even multiverse hypotheses do not deliver an exterior in any satisfying sense. And we saw that, at the deepest level we currently have access to, space itself may not be fundamental, but may emerge from quantum entanglement, from a more basic structure beneath it. Every step in this journey has stripped away an assumption from the original question. Every step has left less of the question intact. By the end, the question is not really a question anymore. It is a kind of artifact, a reminder of how human intuitions work, a fossil of the brain trying to fit reality into the shape of a container. So, if I cannot answer the question, what can I leave you with? Here is the new question. The question that takes the place of the old one. The question that is, at this point in cosmology, the actual frontier. What is space? Not what is the universe expanding into. The expansion is internal. The expansion is a change in the metric, or a change in the entanglement structure, that gives rise to the metric, or some deeper version of either. The expansion is a property of the geometry, not its motion through some larger arena. The into is gone. So the question becomes, what is the thing that is doing the expanding? What is the geometry, the metric, the structure that is changing? What is space at the most fundamental level? Is it a true fundamental entity with its own irreducible existence? Is it an emergent pattern in something more basic, like quantum entanglement? Is it something we have not yet imagined, some structure that does not fit into either of those categories? The honest answer is we do not know. Cosmology, as an empirical discipline, has made enormous progress in describing how space behaves at the largest scales. General relativity tells us, with extraordinary precision, how the metric responds to matter and energy, how it evolves over time, how it produces the universe we observe. Quantum field theory tells us how the smallest constituents of reality behave at the smallest scales. But the union of these two frameworks, the question of what space and time are at the deepest level, the question of what reality is made of, is still open. It is the central problem of theoretical physics. It is what people are working on right now, today, in offices and labs and chalkboards around the world. It is the question that the holographic principle, the entanglement-based picture of geometry, and various approaches to quantum gravity are trying to answer. We are, in other words, at a moment where the most familiar feature of reality, the very space we live in and look out at and call home, has become the great unknown, the thing you have spent your entire life standing inside, walking through, falling asleep within. That thing is, at the deepest level, a mystery. We do not know what it is. We do not know whether it is fundamental. We do not know what it emerges from, if it emerges. We do not know why it expands the way it does, or why its energy is what it is, or why the rate of its expansion has the value it has. The thing under your feet, behind your eyes, between your hands, is something we are still learning to describe. That is, in some ways, more astonishing than any of the specific results we have talked about. The galaxies receding, the infinite or wrapped geometry, the horizon erasing the cosmos, the accelerating expansion, the vacuum energy mismatch, the entanglement-based emergent space. All of these are extraordinary findings, but the thread that connects them all is that the universe, at its most basic level, is not yet understood. We have spent thousands of years building up our intuitive picture of reality, and modern cosmology is, in a real sense, in the process of dismantling that picture and replacing it with something we do not yet have the vocabulary to describe. So when you next look up at the night sky, on a dark night, somewhere away from city lights, and you see the band of the Milky Way arcing overhead, and the stars scattered across it like grains of pale fire, and the deep blackness between them, and you think, there it is, that is the universe. I want you to remember something. The blackness is not empty. The space between the stars has structure. The geometry you are looking through is changing, expanding, accelerating, creating horizons. The light reaching your eyes has been traveling for years or millennia or millions of years, stretched by the metric expansion as it came. And the very nature of what you are looking through, the space itself, may not even be a fundamental thing. It may be something deeper, something stranger, something that, when we finally understand it, will change everything we thought we knew about what reality is. The question that started this whole video, what is the universe expanding into, did not have an answer. It could not have an answer, because the question, in its original form, did not match the structure of the universe we live in. We came looking for a container and found a self-contained geometry. We came looking for an edge and found a fog. We came looking for an outside and found that the inside might not even be the bottom layer. The question did not have an answer because it was not the right question. And the question that takes its place, the one we are still working on, the one we may not answer in our lifetimes, is just 3 words. What is space? That is the real mystery. That is the next horizon. And until we figure it out, the familiar thing you have been standing inside your entire life, the thing you breathe through and walk through and fall through when you trip, is, in the most literal sense available, the unknown. The most ordinary thing in your experience is the most extraordinary thing in physics. And the universe, in its quiet, internal, self-contained way, keeps expanding, not into anything, but into more of itself, becoming more of what it already is, while we sit on a small, wet planet around an average star, in an ordinary galaxy, looking out at the slow, patient, geometric unfolding of a reality whose true nature we have only just begun to glimpse. The question did not have an answer, because it was not the right question. And maybe, if we sit with that long enough, the right question will finally come into focus. And then, at last, we can begin again.